If the propeller is allowed to windmill, the forces generated will cause it to try to unfeather itself. Moving the propeller blades a few degrees below the feathered position will cause the propeller to rotate, and centrifugal turning moments will tend to move the blades towards a finer pitch. This will cause the propeller to rotate faster, until it comes under the control of the propeller control unit. The propeller control lever of the unit being unfeathered should be placed in line with that of the operating engine or engines, and where fitted, the feathering lever should be reset. This allows the speeder spring to push the landed valve down. It also helps to minimize the yaw which will inevitably accompany the effect of unfeathering. Pressure oil can now be directed to one side of the pitch change mechanism to move the piston towards a finer pitch, and coarse pitch oil will be allowed to drain from the other side as it does so. The feathering button should now be pressed. This starts the feathering pump running, which will supply the pressure oil to the pitch change mechanism to move the blades away from the feathered position towards fine. Once the propeller starts windmilling, the feathering button should be pulled out. Pulling out the feathering button overcomes the holding coil. When the contacts of the feathering button are opened, they break the supply to the solenoid relay, the contacts of which are supplying the feathering pump. Thus the feathering pump stops. The rest of the restart drill is accomplished in accordance with the aircraft operating manual. To reduce the workload on the pilot in the event of an engine failure, some propellers are equipped with an auto-feather system. The system is normally active during takeoff and cruise conditions only. For example, on a turbojet engine, with the high-pressure fuel cock open and the power lever set to high power, a signal of low torque from the engine torque meter system will automatically feather the propeller. Should either of these conditions not be met, the auto-feather system will be rendered inactive. This diagram shows an auto-feather system installed on a typical double-acting propeller arrangement for a turboprop engine. It consists of an additional oil pressure line supplied from an electrically operated feathering pump to the underside of a valve lift piston in the feathering mechanism. Control over this oil pressure is provided by an electrically operated solenoid valve. In the event of an engine failure, and provided the engine controls are set to the high-power configuration, a low torque signal will complete the auto-feather circuit and energize the valve lift solenoid and feathering pump. This delivers an independent supply of feathering oil to the valve lift piston, which raises the landed valve to the coarse pitch position. The high-pressure oil supplied by the feathering pump is now fed to the coarse pitch side of the pitch change piston, pushing it onto the feathering stop. As the piston moves, it displaces the fine pitch oil to return. The feathering stop is fitted within the pitch change mechanism, the position of which allows the propeller blades to take up a position edge-on to the aircraft airflow, where they will generate zero aerodynamic force in either direction. The propeller should not now windmill. The propeller control unit incorporates a flight fine pitch stop solenoid, which controls a supply of high-pressure oil to a flight fine pitch stop mechanism in the propeller pitch change cylinder. When the solenoid is energized, oil pressure is directed to withdraw the flight fine pitch stop, thereby allowing the pitch change piston to move below the flight fine position and into the beta range. When the solenoid is de-energized, oil pressure is removed, and the flight fine pitch stop is engaged by spring pressure. Use your mouse to press the repeat button, which will enable you to see the removal of the flight fine pitch stop again. Most turboprop engines are provided with a system of propeller control which is defined by alpha and beta ranges. The alpha range is used at high speed, during the takeoff run, in flight and during the initial high-speed part of the landing rollout. The alpha range is selected by moving the engine power lever to a position at or above flight idle. The beta range is used on the ground only. It's selected during the landing roll by first removing the flight fine pitch stop, or FFPS, which was previously engaged to prevent the blades moving to ground fine pitch in flight, and then moving the engine power lever to a position below the flight idle position. On systems not equipped with a hydraulic flight fine pitch stop, the power lever is moved through a flight idle detent or gate. With the propeller blades functioning within the alpha range, their pitch is controlled automatically by the propeller control unit, whilst within the beta range their pitch is controlled by the operator's movement of the engine power lever. In most aircraft, the selection of the beta range is made by movement of the flight fine pitch stop, the FFPS lever. Alternatively, in some systems the selection can be made via the condition lever, that is the RPM lever, itself. A warning light, usually blue or amber, illuminates whenever the flight fine pitch stop is disengaged. Additionally, other warning lights may be provided, which illuminate whenever the propeller blades are moved below the flight fine pitch position, that is, into the beta range. While the aircraft is taxiing, there is insufficient RPM available to bring the propeller control unit on speed, and it's therefore unable to take control. Propeller RPM is controlled by movement of the engine power lever within its range below flight idle. As power is applied for takeoff, the flight fine pitch stop lever is forced into the flight position by the action of moving the power levers to the takeoff power position. The FFPS light and/or beta lights are extinguished. As the pitch of the blades coarsens to allow the propeller to absorb the increased torque being produced by the engine, the piston in the pitch change mechanism moves into the flight pitch range, or alpha range. This allows the flight fine pitch stop to engage under spring pressure, thereby preventing the piston from moving below the flight fine pitch position. There is now sufficient RPM available to bring the propeller control unit on speed and into a controlling condition. Many turboprop aircraft, and a few high-powered piston-engined aircraft, are provided with a means to allow the operator to select a superfine pitch, or to aerodynamically reverse the pitch of their propellers, or even in some cases to do both. In the case of a superfine pitch selection, a fixed abutment stop in the pitch change cylinder allows the piston to take up a position at or near 0 degrees. This is known as a disking position, and is used for starting and initial acceleration of the engine, and for aerodynamic braking during the landing roll. Superfine pitch is commonly called ground fine pitch, and its position is several degrees finer than the finest pitch available in flight, which is called flight fine pitch. The propellers of more modern aircraft may have a much greater range of blade movement in the beta range. The range can extend from around plus 8 degrees to minus 30 degrees pitch, which is full reverse. The beta range of this type of propeller is selected in a similar manner, and at the same point in the landing run as the previously discussed system, that is, during the high-speed initial part of the landing rollout. In this case, however, the braking effect obtained from the selection of reverse pitch is much more effective than that which would result from merely the selection of ground fine pitch. With the propeller in reverse pitch, the forces on the propeller blade are as shown here in the small diagram on the right of the screen. As you can see, in reverse pitch, the forces generated by the propeller will produce a braking effect to actively decelerate the aircraft after landing. On landing, the flight fine pitch stop lever must be moved to the disengaged or ground position before the engine power lever can be moved below flight idle. On systems not equipped with the removable flight fine pitch stop, the power lever must be moved through a fixed gate or detent. On some aircraft, microswitches, which sense that the weight of the aircraft is on the wheels, ensure that this selection cannot be made in the air. Once the power levers are moved below flight idle, the propeller blades move into the ground fine pitch range, and the propeller control unit relinquishes control. Propeller RPM is now controlled by power lever movement. The forward velocity of the initial landing roll, combined with low RPM and low blade angle, produces a zero or negative angle of attack. This reverses the total reaction produced by the propeller, which acts to slow the aircraft in its landing roll. This condition is known as disking braking. Propellers which can have their pitch angle made even more negative are known as fully reversing propellers. As the power lever is moved further rearwards into the reverse pitch range, the blades move into the negative pitch position. The reversed total reaction produced now increases. This exerts increased load on the engine, so engine power is increased in order to maintain a constant RPM. The engine power and reverse airflow through the propeller is now being used to slow the aircraft down. This condition is known as power on braking.